freshman stepping onto the huge campus of NTU, have you ever wished for a sophisticated tool or a cutting edge AI system to assist you in identifying your location and navigating your way around? My name is Abhinaya, and today I present to you my final year project titled Visual Localization on the NTU campus. Over the past year, I've had the honor of working under Professor Lin and Mr. Huzi, delving into two image retrieval based visual localization techniques that will be discussed in this presentation. The aim of the project was to study the effect of semantic segmentation in visual localization and NetVLAD and APP-SVR as potential solutions for visual localization in an indoor location like NTU. Semantic segmentation information is used to identify the informative and non-informative or shadow sections of an image. This information was utilized to generate attention for VLAD computation in the NetVLAD pipeline. Visual place recognition is crucial for self-navigation and object localization. Amongst various visual localization techniques, image retrieval-based techniques require efficient, low-cost representation of images, accounting for dynamic foregrounds, changing viewpoints, and weather conditions. NetVLAD generates a vector of locally aggregated descriptors or a VLAD representation of the image using a trainable layer appended to popular computer vision architectures such as VGG16 or LXNet. To address informative and shadow areas such as dynamic foregrounds, moving people, vehicles, vegetation, etc., we introduce semantic information-based attention in an attention pyramid pooling scheme. In this project, we explore the potential applications of NetVLAD and APP-SVR as visual localization techniques at NTU. NetVLAD was implemented as a pooling layer on top of the VGG16 architecture, and triplet margin loss was employed as the loss function. The NetVLAD layer uses clustering and soft assignment to generate VLAD representations of each data point. 64 cluster centroids were learned to create a final representation of dimensions 64 by 512. For each query, its VLAD representation is computed and compared using Euclidean distances. To create an attention-aware feature embedding, we implemented the local attention module of APP-SVR, which takes semantic information generated by a pre-trained, state-of-the-art semantic segmentation model, mask deformer. The semantic information is used to initialize clusters and shadow centroids and generate attention, which accounts for moving foregrounds such as people and vehicles, and seasonal aspects such as vegetation and skies. The implemented semantic-based attention proves to be similar to the SRALNet or Semantic Reinforced Attention Learning Network pipeline. Therefore, the results obtained from the experiment are compared with NetVLAD, APP-SVR, and SRALNet. The main quantitative measurement of the model's performance is the recall rates, which indicates the percentage of queries that can correctly retrieve an image from the database at n potential positives. In the first experiment with NetVLAD, the obtained recall rates with the Pittsburgh 30K dataset are comparable to the values reported by the original author. To test the model's generalizability, its performance on the Tokyo Time Machine dataset was also evaluated. The recall rates at 1 and 5 are comparable at 86.1%, but there is no significant increase in recall rates for higher values of n. The integration of semantic information was first tested with the visualization of attention maps for sample input images. Attention maps generated for different numbers of shadow centroids were visualized to identify the optimal number for training. Based on this visualization, 4 shadow centroids were chosen as the optimal number. The recall rates were compared to APP-SVR and SRALNet. We also see a clear improvement in recall rates at 1 from 0.8381 to 0.8563 as compared to NetVLAD and the addition of semantic information. This proves the hypothesis that semantic information can complement and improve performance in the visual localization task. A query visualization tool was developed to visualize the query, the retrieved images, and whether they were retrieved correctly or not. Studies were conducted to evaluate the model's performance under changing illuminations. The model is able to identify buildings and roads while filtering out vegetation, skies, and moving vehicles, indicating its robustness to changing illuminations and dynamic foregrounds. The pipeline generates mildly noisy but promising attention maps for locations within NTU. Therefore, both implemented models can be considered as potential solutions for visual localization at NTU. To test the application of the models for visual localization at NTU, a sample dataset of the North Spine Plaza was created with images taken from Google Search. A mobile application POC was developed which allows users to take or upload photos and use the model to retrieve images from the previously created dataset. Such an application will greatly benefit freshmen and others alike in navigation within campus and to learn more about various iconic locations within NTU. Moreover, the potential for extending visual localization techniques to metaverses presents an exciting opportunity to create a game-based interface that motivates users to explore and discover new areas within the virtual world. Overall, these applications have the potential to enhance user experience and engagement in both physical and virtual environments.